So the final transformation for these geometric transformations is the dilation. And a dilation is scaling a shape, whether up or down, by a factor of n. This is not rigid because you're not preserving the lengths of the shape anymore. You're scaling them up or you're scaling them down, they're not staying congruent. And so if n is a number, if the thing that you're multiplying is a number larger than 1, your shape is going to enlarge. If n is a number between 0 and 1, like 1/2 or 1/3, your shape is going to reduce. So if we look at this example here, we have obviously an example of our prime image being an enlargement of our pre-image. And if we look at our distances, the original yx distance here is 3. The new yx prime distance is 6, so we have a enlargement, a scale factor of 2. Now one thing we'll notice is that if you draw a line from x prime to x and continue it down, and you do that from y prime to y and z prime to z, they're all connecting at the point of dilation, where they're all coming out from. So just like with rotations, dilations do not have any specific kind of notation for them. It's a written description. You're going to be told to dilate the figure by a certain amount from a certain point. Dilations are similar to each other, but they are not congruent to each other. They look the same, but they're different sizes. The image lengths of the prime image, the way that you get that measurement is by taking the pre-image lengths and multiplying it by the scale factor. And the distances within the shape are the same. So C here being that point that it's coming out of, C to Z and C to Z prime is a scale factor of 2. And then XZ, so the distance from X to Z and the distance from X to Z prime is also a scale factor of 2 to get from one to the other. The center of dilation, that C that's being referenced, the center of dilation is the fixed point that your figure is expanding from. So in this case it is the origin, because we see that they're all coming out from there. So you can always draw a line connecting the dots and it will lead you straight back to the center of dilation. So as we look at these two first example problems, the first one says that quadrilateral JKLM prime is a dilation of JKLM. We want to know what is the scale factor and if it's an enlargement or a reduction. So looking at the diagram, we see the white one is JKLM, the blue one is JKLM prime. That means we went outwards to the blue one, we enlarged the image. So the question is, what was that scale factor? To find scale factor, you do the same thing you would for distance or anything else. You take the second number, whatever came after the movement, and you divide it by the first number. So 18, where I went to, divided by 12, where I came from. The prime divided by the pre. And it gives you 3/2 or 1.5. So my scale factor here is 3/2 as big as the original image. For our second one, we are given a triangle ABC. A is at 2, -1, B is at -1, 2, and C is at 3, 0. And we want to know what are the vertices of ABC prime after a dilation of a factor of 2 is applied. So because it gives us nothing else besides just saying that it's a dilation of 2, all we have to do is just take the original vertices and multiply them by 2. So our A goes from 2, -1 to A prime 4, -2. B goes from -1, 2 to -2, 4. And then C goes from 3, 0 to 6, 0, which we see plotted. So we just take our original vertices and we multiply everything in it by 2, giving us our new triangle, which we can see not only is twice as large as the original white one, but also is twice as far away as the original white one from that fixed point of dilation, the origin. So if we're not dilating from the origin, we have to do basically what we did for rotations. We have to identify what it is that we're expanding from, our center of dilation. We have to move that center of dilation back to the origin. We have to apply all that same movement to the other points that we're actually dilating. We dilate everything like normal, so just do the multiplication, and then we move everything back. So just like with rotations, we undo it, apply it, and redo it. So our example is we want to find the image, what comes after the dilation, of A when it's dilated by a factor of 6 from the point -4, 9. So because we're coming from this point, we need to undo that point. So -4 we add, and 9 we subtract. And this gives us 9, -10. Now we do the dilation, so we multiply everything by 6, giving us 54, -60. And then we need to redo the point back into it. So instead of adding and subtracting, we do what the actual point is. So we subtract 4, we add 9, giving us our final answer of 50, -51. And then that is A prime because we came from A. So as we look at these three examples, it's the same idea. So the image of A, -3, 4, when dilated by a factor of 1/2, which is a reduction from the point 1, -2. So because it's 1, -2, we subtract 1 and add 2, giving us -4, 6, which then we multiply by 1/2, giving us -2, 3. And then we redo our point back into it. So we add 1 back in, subtract 2 back out, giving us a final answer of A prime being -1, 1. As we look at the second one, B is at -2, 0, and we're finding the image after it's been dilated by 2 from the point -3, 1. So just like last time, we're going to add 3 and add the 1, undo the point that we're going from. That gives us 1, 1. Then we're going to multiply it by that scale factor of 2, giving us 2, 2, and then we're going to redo the point back into it. So subtract 3, subtract 1, so final answer of also -1, 1. So B prime, -1, 1. And lastly, image of C, 1, -5, when dilated by a factor of 2/3. So this is also a reduction, 2/3, from the point -2, 1. So we're going to undo it. It gives us +2 -1, so 3, -6. Multiply it by that 2/3, giving us 2, -4. And then reintroducing -2 + 1 back into it. So final answer of C prime being 0, -3.